All right, physics reaction video number 42, which reminds me of my childhood, reading Douglas Adams books. So we'll see if today we learn the answer to life, the universe, and everything.
All right, hello AP Physics 1 students. It is time to finally wrap up our unit on dynamics, and today we're going to do that by talking about inclined planes.
Right.
So, what is an inclined plane? Now, an inclined plane...
So I did a search, and I filtered for things only in the last week. So I'm trying to understand why an AP Physics 1 class would be doing inclined planes now. I'll have to dig into that. I mean, nothing wrong with this content, of course, but I was just thinking that in January we'd be seeing something else. I mean, I don't exactly know how that curriculum works. I did hear, though, that they took out, what was it, waves and optics from the AP Physics 1 test, so I don't expect to see any videos about that. But anyways, we'll do inclined plane here.
What is an inclined plane? Now, an inclined plane is just, it's basically just a ramp. So because it's tilted any form...
Okay, so she's using Google Slides, which has that awesome laser pointer thing. I think the laser pointer thing is awesome. And so if you're making a recording of it, so this is going to be fantastic. Well, there's a little bit of a delay here. Anyways, the recording will be fantastic, but recognize, of course, that none of these laser pointer things are permanent. And so it's interesting to realize that this is really meant to be either watched or to be live. And of course, thank goodness it's not leaving a trail, like a permanent trail, because it would just make everything hard to read. But I also just wanted to comment that I don't know why we don't just say ramp. Inclined plane, it sounds so complicated. It's just a ramp. I love that. Back up just a little bit so we can see that laser pointer stuff again.
is just, it's basically just a ramp. So because it's tilted, any force acting on an object on the inclined plane will have a horizontal and vertical component. This includes friction, normal force, etc.
Cool.
And yeah. So here's the thing about our inclined planes. We can't really use our normal coordinate system to do it because, as you can see, if we have our y-axis just going straight down and our horizontal axis just going straight left and right, there's going to be some problems with the forces being applied to an object. So as we can see, our normal force is going to be diagonal, our friction is going to be diagonal, and so is our acceleration. Now this becomes a problem because now they have to be broken up into x and y components, and that just makes calculations real.
So I love what you're saying. I talked about this a number of videos ago, that you can do this. But why would you? I also just want to make a comment about the stupid little bar that you can see in Google Slides. I find it very frustrating. I'm sure she finds it frustrating too. It doesn't go away nearly fast enough, and I have not found the keyboard shortcut to make it go away. It does go away. In fact, it looks like it's just now starting to fade away. But you know, physicists, teachers, we use the entire screen space. In fact, I'm clearly blocking some stuff in my face right now. So I find that extraordinarily annoying. Hey, and look, here's the word annoying. But anyways, I really liked, at first I was like, oh, she's saying it can't be done. But then I loved how she said, well, good Lord, you could, but look at all these things that are diagonal. The only thing that works in this coordinate frame, of course, is gravity, which is straight down. Also note that this, wherever she found this picture, didn't get the tails of the, actually got the tails just fine, it just got the dot in the wrong place. I think that's really interesting. All right, let's back it up. And go again.
X and Y components, and that just makes calculations really annoying.
There, the Google Slides thing went away.
To solve this, all we have to do is rotate our coordinate system. If we rotate our coordinate system so that our axis is parallel to the surface of the ramp and the y-axis is perpendicular, this becomes much less of an issue. Now, as you can see, our normal force is perpendicular to the surface of it, our friction is parallel to the surface, and our acceleration is parallel, and now only our force of weight has to be broken up. And how are we going to do this, I hear you asking? Well, we got to use some trigonometry.
Ooh.
As I'm sure you all noticed, we have a right angle here, which means right triangle, so the trig's going to be super easy. And if an object with a mass m is on the ramp...
Let do you think about that statement? You notice that it's a right triangle, so the trig is going to be super easy. I think some students would say, of course it's a right triangle. That's the only thing we know how to do trig on. But of course, trigonometry has all kinds of interesting stuff that you can do. But yeah, we're going to have right triangles all the time here. Let's see, why does this have to be a right triangle? You could make this anything you wanted to. Because the normal force has to go perpendicular to the surface. So the normal force is why we want this to go like that. And then, of course, to be at this angle here. And then, of course, the motion is down here. So that's why this is a right angle. And so, some people have wondered why I hate the sine trigonometric function. Look at this, poor sine. Always has to be pushed to the opposite, whereas cosine gets to be adjacent. Bully. Cosine is a bully.
Then the force of gravity has two components. We have our component that's parallel to the ramp, which is right here, or right here in this little picture, which is going to be mg sine of theta, or force of weight times sine of theta. And then we have our element that's perpendicular to the ramp, which is right here, so mg cosine of theta.
I just want to pause here and talk about the value of using an image from, I'm guessing this is from the textbook. It kind of looks like this is a picture, sort of looks like there was some distortion here. Why do I like that? Because, of course, this is not that hard to draw on your own. But if that's what your students have access to, so this is the first reason, if that's what your students have access to, it's really great to show it to them. And secondly, it just gets everything right. Everything looks good. People really pay attention to typesetting, all of that stuff. So I think that making use of these images is great. You can tell it's a picture of a textbook because you can see a tiny little bit of text flowing through from the previous page, or I guess next page. I guess it could be previous or next. So I really like that. I loved how she broke down the trigonometric components here of the force of gravity. So of course everyone knows that once you've done that, the rest is relatively straightforward. So let's see what happens next.
Now, because this is parallel to the ramp, the force driving the block down the ramp is parallel, which means we're going to be using our mg sine of theta. Now, our mg cosine of theta is perpendicular, which means that's mostly going to be used for our normal force, because as we know, normal force is perpendicular to the surface. Alright, let's go ahead and look into an example. So, a block slides down a frictionless inclined plane at a 30-degree angle. Find the acceleration of the block. Alright? So what we're going to do is we are going to draw a picture now. We have our 30-degree angle right here, and we have our force of weight broken into our perpendicular and parallel components.
So again, this is Google Slides, and so it's actually possible to draw on Google Slides. You have to insert a drawing, but clearly this is an imported picture. You can tell because of the anti-aliasing stuff that's going on here in the edge. This, I'm guessing, is now her handwriting. So a big question, right? Like, why not continue to use the image you had before? My guess is because she really wants to annotate this and found it easier in whatever drawing program she had to do the annotations. Plus, she was able to label this now as 30 degrees. And perhaps this really is 30 degrees. Let's see if that's 30. That'd be 60. This is probably close to 30 degrees. Let's see. So the sine of 30 degrees is 1/2. So is this half as long as that? Yeah, this is pretty dang close to 30 degrees, actually. So I think redrawing it in that case is going to be super useful.
So we know that our force that's driving it down is going to be mg sine theta because it's parallel to the surface. Okay? Now, we also know that force equals mass times acceleration, and we can isolate acceleration and just get it equals force over mass. And if we plug in this equation for our force into our acceleration formula, we get acceleration equals mg sine of theta over m. Now, the great thing about this is we have m in the denominator and m in the numerator, so we can just cancel those out. And we get our acceleration equals g sine of 30. Now, sine of 30 is 1/2, so we get g times 1/2, or 5 meters per second squared.
Lots of really good stuff in here. Wow. So first of all, again, Google slide presentations you can share with your students later. You can really futz with where you're going to put your various images. This arrow is quite useful to explain what's happening, but really watching the video is going to help understand how you go from these two down to here. Love hey, how nice it is that the masses cancel. And of course, I always like to pause and say, oh my gosh, the masses cancel. It doesn't matter how much this thing weighs, what the mass of this thing is, they're all going to, every single box or whatever is going to slide down at the same rate. And of course, 30 degrees is nice because the sine of it is so easy. The cosine, of course, is ugly and gross. But then also this, I love this, right? So some of you are like, oh, it's not 5, it's 4.9, right? But I was talking to some other folks about how if you just use 10, you can so rapidly do stuff with folks, and you're just not that wrong, right? What are you? You're off by 20%, that's not horrible. And then finally, just noticing again the typesetting, you heard me talking a few times ago about occasionally some books and texts and teachers want to do m(s to the negative 2). And so I think that having the slash here, I'm really starting to think about this, right? Like when I first saw the s to the negative 2, I was like, I'd rather have the slash. But there's three things, right? You could do m over s squared. The slash, I think, I think it can be confusing. I don't think it is in this case, but I think it could be. So I'm really starting to think again about the way to express these units. So 30 degrees is all it takes to get this thing to go, to accelerate half as much. Actually, a better way to say it is that when you're going straight down, so that'd be 90 degrees. When you're going straight down, you have to come down by 60 degrees before you finally cut it in half. That's more interesting to me, I guess. All right, cool.
Easy enough? All right. We are going to go add on to this example a little bit more now.
Excellent.
Example 2. Find the acceleration of the block in the previous example if the coefficient of friction is 0.03. All right. Once again, we're going to draw a picture, and now notice that we have more forces being applied.
So I love this extension, right? Because at first you're like, okay, just tiny little bit of friction, I'm going to subtract a little bit and be done. And yet all of a sudden, what? We got to do this component now? What the heck? And it's because, of course, we have to figure out what the normal force is. So let's keep an eye out, right? Is mass going to cancel here too, right? Because that's really interesting. At what point does the actual mass matter? At what point does what planet you're on matter? Clearly what planet matters because we're still using G in this. G's not canceling. You know that G cancels on occasion. For example, the height of a hill that's high enough to let a loop-de-loop go, G turns out canceling, right? So apparently those work on any planet you put them on. So let's watch to see if M cancels. Yeah, but the really interesting point is even though the frictional force is in this one direction, it makes it seem like it's a one-dimensional problem, which is fantastic, and yet we have to go to the other dimension to figure out some of the crap. So that's really interesting.
So we have our force of weight sine theta that's driving it down, our force of friction that's opposing that motion, and our normal force, which is just going to be the same as our force of weight times cosine theta because it is perpendicular to our surface. All right, we also know that our theta equals 30 and our coefficient of friction equals 0.03.
So I'm noticing something really interesting from a technological point of view. I'll back it up so you can see it, but watch the circle she draws here. It actually gets polygonated. Is that a word? You can actually see some facets of the trail. And my question is whether it looks that way when you're live, number one, whether it looks that way when you're live and recording your screen, number two. And clearly we know what it looks like for us because I'll bet you it looks, if you're not recording your screen, I'll bet you it looks super, super smooth. So that it's just a technological question. So let's back it up and see if we can, yeah, you can see it right here. That is really fascinating. I wonder, given the fact that there's this gap here, maybe you do see it live. Huh. That's really interesting.
Our theta equals 30 and our coefficient of friction equals 0.03. So first thing we're going to do is we're going to solve for our friction. Or at least get a formula for our friction.
Oh yeah,
so we
M's definitely canceling.
that friction equals mu times normal force. And we, as we said earlier, our normal force is just going to equal force of weight times cosine theta. So we have...
Just pausing here. A lot of people remember this as F equals mu times N, and they call it the fun equation. So she's being much more explicit about the subscripts here. Interestingly, she's not putting vector symbols over these, but that's because she has drawn all of these. We know exactly what direction they go. So, you know, vectors have two pieces of information, how much and what direction. Well, if your diagram has the direction and really does take care of that well, I don't have a problem with but just doing magnitudes over here. That's pretty cool.
mu times force of weight cosine theta. And we also know that force of weight is just mass times gravity, so we get mu times mg times cosine of theta. Alright, now, to find our acceleration, we need to use our net force, so we know that that's going to equal our force driving it down the ramp, or our force of weight times sine theta, minus the force that is opposing that motion, or our friction. Now we're just going to go ahead and plug in what we got for our friction, and since it's force of weight sine theta, we can substitute in mg for force of weight, so we get mg sine theta minus mu mg cosine of theta. Now, one thing you're going to notice is that we have an mg in this one, and we have an mg in this one. So, as my calculus teacher likes to say, it's time for our favorite F word, factoring. So we can just take our mass times gravity and put it outside of the parentheses, so we have mg times sine of theta minus mu cosine theta. Now, if we look right over here, we have our force equation again. So we have force equals mass times acceleration. Once again, we're going to isolate acceleration, and we get acceleration equals force over mass. Now, if this is our net force, we're just going to plug it in right over here.
So I'm just going to pause. So it's so interesting to me. I noticed when this question was first posed, it didn't really stipulate static coefficient versus kinetic coefficient of friction. And when I look at this, I can definitely make this be 0. In fact, I don't even think it matters what mu you use, because I think that if you wanted this to be 0, there would always be a theta that'll make this be 0 independent of what mu you choose. I'm pretty sure. Yeah, because tangent goes from 0 all the way up to infinity. Yeah, so there's going to be an angle. So there's going to be an angle where this is 0. But of course, the problem with sort of static versus kinetic is that you can make the kinetic be 0, which is, she's doing kinetic here because the thing's moving. But that's actually, you can make it steeper and have the static still not be broken. It's also interesting to think about sine being a supernormal function, super nice and not a bully, right? If the angle's small, it's small. It kind of makes sense. Cosine's like, if the angle's small, I'm going to be big, right? It's just a jerk. So recognizing that as the angle grows, this is going to get smaller, but this is going to get smaller too because of the negative sign. So fascinating to think about like how the extensions you can do with this. Here the m's, of course, are going to cancel, and we're going to get a result. What was mu? Oh, it's very, very small, 0.03. Okay, so this term's going to be pretty dang small. So this is not going to be a whole lot different than the answer we got before. Let's see. So we got 5 before. I'm going to say 4.5.
And we're going to get our acceleration equals mass times gravity times sine theta minus mu cosine theta over m. Now we have m in the denominator. I hate this little tab at the bottom. And m in the numerator, which means it's time to cancel. We cancel out our m's, and we get our acceleration equals
4.5.
g sine theta minus mu cosine theta.
4.5.
Now, all we have to do now is we have to plug in. So
What?
g is 10 sine of 30 and cosine of 30, and our mu is 0.03.
How did this change so much? I was thinking this was such a small number that it was just going to, who cares about this term? So square root of 3 over 2 is like 0.9 or something. So it'd be like this digit here. Oh, the 10 was factored out. Urgh, dang it.
We get 10 times 1/2 minus 0.03 times rad 3 over 2, because that's our cosine of theta, and we get that equals 2.4 meters per second squared. Alright, so I hope that was helpful.
All right, I'm just going to back it up here just so we have something to stare at. So I really, really liked a lot of things in here. First of all, I loved this use of Google Slides. Google Slides can be super, super interesting. And if you go and do your recording in Google Meets, which is a possibility, you also get automatic captioning. So that's a super interesting idea. I've been thinking about that for my class that I'm about to teach. I usually use some other fancy screen recording software like what I'm using to do this. But if Google Meets is going to do automatic captioning for me, maybe that's a smarter thing to do and just record my screen while I do that. Or I guess just have Google Meets do the recording. So anyways, I really liked how she set this up. Talked about how why we have to shift the the frame of reference. I liked how she just very, very methodically went through this stuff. No question about it. I'm also fascinated by the laser pointer, which I thought was super, super cool. And I don't know, I just thought this was a really great presentation on this material. All right, everybody. Well, I hope you have a great day. And remember, physics teachers are awesome.